Hello, and welcome to Comba University. In this module, we will cover the RF link budget. The RF link budget is the most important part of designing a radio communications system and is crucial when implementing in-building public safety DAS systems. We will learn about what a RF link budget is and how to perform the proper calculations. Furthermore, we will cover the three main types of link budgets required to properly design and implement an in-building public safety radio communications system: the downlink link budget, the uplink link budget, and the uplink noise link budget, and we will work through an example of each together. The RF link budget is the most important tool for system-level design of wireless systems. Link budgets are used in the development of new wireless systems, as well as when installing a specific wireless link. An RF link budget in a radio communication system is a calculation that accounts for all the gains and losses from the radio transmitter to the receiver. The RF link budget will include the transmitter output power, cable losses, antenna gains, path loss, amplifier gains, antenna distribution losses, and building losses. It's essentially a signal strength balance sheet used to guide the design and dimensioning of communication systems, ensuring that the system will provide sufficient radio coverage and signal quality, even under worst-case conditions. Here we have a visual representation of a basic RF link budget, showing how signal power changes as it travels from a transmitter to a receiver through all the components in a radio system. The goal of the link budget is to determine the received power level at the receiver. Let's go through each part of the link budget from left to right to have a better understanding of the components. The transmitter is a radio or base station generating the RF signal with a fixed amount of output power. The transmit cable connects the transmitter to the antenna and will introduce a cable loss. The transmit antenna will add gain and emit the signal. The signal will then travel through air and experience free space path loss, which increases with distance and frequency. The receiving antenna captures the transmitted signal and provides antenna gain. The receiving cable connects the receiving antenna to the receiver and will introduce a cable loss. The end device that detects and demodulates the incoming signal is the receiver. The power level at the input of the receiver is the received power. To calculate the received power, we simply start with the transmit power and add and subtract all the gains and losses before the receiver. In this example, the formula for received power is as follows. The received power is equal to the transmitter power minus transmit cable loss plus transmit antenna gain minus free space path loss plus receive antenna gain minus receive cable loss. This is just a generic example of an RF link budget. Next, we will discuss the link budgets that apply to in-building public safety BDA systems. For every in-building public safety BDA system, or any over-the-air BDA system in general, there should always be 3 RF link budgets performed to provide clear evidence that the system will operate within the required specifications. These RF link budgets are as follows: the downlink link budget, the uplink link budget, and the uplink noise power link budget. Each of these link budgets can also be divided and viewed from the in-building side and outdoor or macro side. Link budgets are also used to optimize the estimated BDA gain and power levels that will be required to meet signal strength and noise requirements. Furthermore, the link budget is used to guide the design of the antenna layout of the DAS system, estimating the coverage each antenna will provide. There are many forms of link budgets. Simple link budgets can be performed by hand using formulas or by using calculator tools built in Excel or other programs. The most common link budget softwares that are available are IB-Wave design software and RANPlan design software, which are basically very sophisticated link budget calculators, which can provide a visual coverage heat map of estimated received power levels. Many AHJs and licensees throughout the USA and Canada require a link budget and coverage heat map, which can only be provided by these types of software applications. It is important to understand that these software applications are nothing more than link budget estimator tools. Even though they do a lot of the work for you, it is important to have a strong background of understanding RF link budgets to check the work the program produces and make sure it is accurate. Furthermore, link budgets are only estimations. During the installation and commissioning phase, real-life measurements are made and can be compared to the link budget estimation. Based on the comparison, final adjustments can be made to optimize the BDA settings and provide optimal coverage. Without understanding the math involved in a RF link budget, one cannot safely install a signal booster or BDA. Every signal booster changes the dynamics of the macro world. It is the responsibility of the AHJ and licensee to authorize the design, installation, and turn-up of the system. It is the integrator's responsibility to evaluate how the BDA will affect the surrounding macro environment and to determine the appropriate gain and power levels needed to achieve the required coverage without causing interference to the outdoor macro network or designated radio site. The system integrator or BDA operator are required to provide a RF link budget showing the BDA system will work as intended, with margin for adjustments during the installation and commissioning. During commissioning, only minor adjustments should need to be made to optimize the BDA performance and provide sufficient coverage levels. If the initial RF link budget estimated levels are close to the actual field measurements, the BDA operator can be confident the system is working properly. If the actual field measurements differ greatly from the initial RF link budget, the BDA installer and operator can perform further troubleshooting to determine if there are issues with the installation or components in the system. Here is an example RF link budget for an in-building BDA system. This link budget was created in an Excel spreadsheet format using built-in math formulas and shows the in-building side of a downlink link budget, showing the downlink power levels and changes from the BDA to the in-building service antennas. A link budget like this can be used to optimize the design of the in-building portion of a DAS system. For example, it is best practice to design a system with a balanced level of output from each antenna, meaning each antenna is providing approximately the same amount of output power. The directional coupler values will need to be selected accordingly to provide a balanced antenna output. In this link budget spreadsheet, the directional coupler values can be changed by the designer, and they can see how this affects the antenna outputs. This link budget spreadsheet example is a more antiquated way of performing a link budget, as it takes a lot of time to enter the values by hand and optimize the values. Here is an example of a complete BDA system link budget created using Comba's Public Safety BDA Link Budget Calculator, available to customers upon request. This tool estimates downlink and uplink signal strengths and noise levels at key points in the system to ensure that the BDA is properly sized and configured, coverage requirements are met inside the building and at the donor site, noise and gain levels remain within safe limits to prevent interference or instability, and in teat, all system losses are accurately accounted for. Users simply enter their design parameters in the yellow input cells at the top of the sheet. The tool then generates a full downlink, and uplink noise link budget between the donor site and in-building radios. Using these results, designers can optimize BDA power and gain settings to meet system power and noise requirements. This calculator provides a straightforward yet advanced method for link budget analysis. It can also be used to validate IB wave or RAN plan design link budgets for accuracy. Additionally, because certain link budget calculations can be complex or unavailable in programs such as IB wave or RAN plan, tools like this offer a convenient way to fine-tune and validate system designs. At this stage, we will not review all the values in this example, as it will be covered later. This final example shows a downlink link budget generated using IB wave design software. It displays the downlink signal strength at key points in the system, from the rooftop donor antenna to the indoor service antennas, to confirm that the BDA is properly sized and configured, the system meets in-building coverage requirements, gain levels remain within safe limits to prevent interference or instability, and all system losses are accurately accounted for. Designers can also use this link budget to verify that the indoor antenna distribution is properly balanced, ensuring consistent output levels across all antennas. Additionally, IBWave's automation tools can assist in balancing the system and optimizing the efficiency of the RF distribution network. An essential part of the link budget is accounting for passive equipment losses, such as cable attenuation. This slide includes a sample datasheet showing the losses for a typical half-inch coaxial cable across various frequencies. Cable manufacturers usually list attenuation in both metric and imperial units, so it's important to use the correct specification. The metric value represents loss in decibels per 100 meters, while the imperial value represents loss per 100 feet. In link budget calculations, loss and attenuation are interchangeable terms. Calculating the signal loss over a specific length of cable is simple. If we know the frequency and the length of required cable, we can calculate the loss of the cable using the formula. The cable loss is equal to cable length times the attenuation per 100 feet divided by 100. For example, determine the loss for 200 feet of cable at 860 megahertz. From the datasheet, the attenuation at 894 MHz, which is closest to our frequency, is 2.15 dB per 100 feet. Now we can use the formula. The cable loss is equal to 200 feet times 2.15 dB divided by 100 feet equals 4.3 dB. In addition to cable losses, passive components such as splitters, tappers, and couplers also introduce signal loss that we must account for in the link budget. This slide shows a directional coupler as an example. A directional coupler has 3 ports: input, coupled, and through. Datasheets typically list couplers in a series. This specific directional coupler series, shown on the slide, has coupling values of 5, 6, 7, 8, 10, 13, 15, and 20 dB. The coupled port loss equals the specified coupling value, plus or minus the tolerance, while the through port loss is provided in the loss row of the datasheet. Directional couplers are used when unequal power distribution is required between 2 branches of a passive network. On the other hand, equal power splitters, such as 2-way, 3-way, or 4-way, function differently. They divide the input signal evenly across all output ports. In many cases, a rough link budget is created to provide an initial estimate of the required system components. To simplify these preliminary calculations, it is common to assume a through loss of approximately 0.5 dB per coupler. For the exam at the end of this RF 101 course, if a link budget question does not specify a coupler's through loss, use 0.5 dB as the assumed value. If a link budget question does not specify a 2-way splitter's through loss, use 3.5 dB as the assumed value. In addition to accounting for system losses, it's essential to include the BDA gain and maximum output power in your link budget. These values can be found on the manufacturer's datasheet, which typically spans 2 to 3 pages and includes various technical details. For link budget calculations, the most critical specifications are the maximum output power and the system gain. In the example 700 and 800 MHz BDA datasheet shown on this slide, the downlink output power is either 33 dBm or 27 dBm per band, depending on the model. The uplink output power is shared between both bands and rated at 27 dBm. The BDA provides a maximum gain of 90 dB with an adjustable range of 0 to 30 dB, allowing a configurable total gain range of 60 to 90 dB. Now that we understand the key components contributing to system gains and losses, we can perform a downlink link budget. The downlink link budget traces the signal path from the tower transmit antenna to the portable radio receiver, estimating the signal strength received within the building coverage area. Starting on the left of the diagram, the public safety communications tower transmits a signal from its antenna at a fixed power level. This is the starting point of the downlink link budget. The emitted power for a single channel is known as the effective radiated power, or ERP, typically provided by the local AHJ or system licensee. ERP is expressed in watts or dBm. For link budget calculations, all values should be in decibels, either dB or dBm. If ERP is provided in watts, it must be converted to dBm. When multiple channels are active, the total composite ERP can be calculated to ensure the BDA operates within its input and output power limits. Next, we calculate the free space path loss, or FSPL, using the known frequency and distance between the tower and donor antenna. Next, we have the donor antenna. The donor antenna provides gain, specified in the manufacturer's datasheet as either dBd or dBi. Always use dBd as it references gain relative to a half-wave dipole antenna, consistent with real-world antenna performance for typical dipole-based designs like Yagi or log-periodic antennas. Next, we account for donor antenna transmission line loss, which includes losses from the coaxial cable and passive components, such as lightning arresters, between the donor antenna and the BDA donor port. Next, we have the BDA, which amplifies the signal and provides gain in the downlink path. The BDA downlink gain should be optimized using the formula. The BDA downlink gain is equal to the desired BDA output power minus the BDA input power. Following the BDA, we account for passive DAS losses. Because losses between the BDA and each indoor antenna may vary, it's best to calculate and use an average DAS loss in the downlink link budget. Finally, we consider near and far path losses. The near path loss represents the loss between an indoor antenna and a portable radio located close to it, typically within 5 to 10 feet. This radio will experience the strongest downlink signal. The far path loss represents the loss between an indoor antenna and a radio located in the most distant area served by that antenna, resulting in the weakest downlink signal. The far distance depends on the building layout and system design. By determining all the values shown on this slide, you can accurately calculate the downlink link budget. To determine the downlink signal strength received by both the near and far portable radios, we will break the calculation into distinct steps. For this analysis, we'll assume the BDA downlink channel output power is set to its maximum rated value to achieve the strongest possible downlink signal. First, we calculate the BDA downlink channel input power. Next, we determine the BDA's maximum downlink channel output power. Using these values, we then calculate the required downlink gain needed to amplify the input signal to the maximum output level. Finally, we calculate the received signal strength for the near and far portable radios. To calculate the BDA downlink channel input power, use the following formula. The BDA downlink channel input power is equal to the radio tower ERP minus the free space path loss plus the donor antenna gain minus the transmission line loss. To calculate the BDA maximum downlink channel output power, use the following formula. The BDA maximum downlink channel output power is equal to the BDA maximum composite output power minus 10 times the log of the number of channels. Alternatively, if the downlink gain is already known, we can use the formula. The BDA downlink channel output power is equal to the BDA downlink channel input power plus the BDA downlink gain. To calculate the required BDA downlink gain, use the following formula. The BDA downlink gain is equal to the BDA channel output power minus the BDA channel input power. To calculate the received signal strength for the near radio, use the following formula. The near radio received signal power is equal to the BDA maximum channel output power minus the passive DAS loss minus the near path loss. To calculate the received signal strength for the far radio, use the following formula. The far radio received signal power is equal to the BDA maximum channel output power minus the passive DAS loss minus the far path loss. In addition to the channel input and output power calculations, it's important to verify that the maximum downlink composite input power to the BDA does not exceed its rated input limit, which could cause overdrive or saturation. If we know the number of channels used in the radio system, we can easily convert from a channel power level to a composite power level by using the following formula. The composite power is equal to the channel power plus 10 times the log of the number of channels. Now we're ready to walk through a complete downlink link budget example. The purpose of the downlink link budget is to trace the signal path from the tower transmit antenna to the portable radio receiver, estimate the received signal strength within the building coverage area, and verify that the levels meet required performance limits. refer to the diagram on the screen showing a typical public safety BDA system. To complete a full downlink link budget, the following input parameters are required: the number of system channels, the radio tower channel ERP, the control channel frequency, the free space path loss to the donor site, the donor antenna gain, the cable loss between the BDA and the donor antenna, the BDA maximum downlink composite power, the passive DAS loss, and the near and far radio path losses. For this example, the input parameters are listed in the box at the top right of the screen. The number of system channels is 16. The radio tower channel ERP is 50 watts per channel. The control channel frequency is 855.5 MHz. These parameters are typically obtained from the local radio system licensee or AHJ. The donor tower site is located 2.5 miles from the rooftop donor antenna. This distance can be determined using tools such as Google Earth to measure the separation between the project site and the donor tower. The remaining values are based on system design assumptions. In this example, we are assuming a donor antenna gain of 9 dBd, a cable loss between the BDA and the donor antenna of 3 dB, a BDA maximum downlink composite power of 2 watts, a passive DAS loss of 15 dB, and a near and far radio path losses of 43 dB and 74 dB respectively. We'll use the diagram on the slide as our guide, filling in each value as we move step by step from the donor antenna on the left to the portable radios on the right. We'll begin by entering all known input parameters. The missing value is the BDA composite output power. We can't enter a composite power of 2 watts directly, as power levels and link budgets are expressed in dBm. Converting 2 watts to dBm gives 2 watts equals 33 dBm. We'll use 33 dBm as the BDA maximum downlink composite output power. Now we can begin filling in the remaining values. Starting at the radio tower output power, we can convert 50 watts to dBm using the formula. The power in dBm is equal to 30 plus 10 times the log of the power in watts, which gives us 30 plus 10 times the log of 50 watts equals 47 dBm. Although the composite output power isn't required for this step, we'll calculate it for reference. The composite radio tower output power in watts can be found using the formula. The composite radio tower output power in watts is equal to the power per channel in watts times the number of channels, which gives us 50 watts per channel, times 16 channels equals 800 watts. Next, we convert the total power from watts to dBm using the standard conversion formula, which gives 800 watts is 59 dBm. Alternatively, we can calculate the composite power directly in dBm using the composite power in dBm is equal to the power per channel in dBm plus 10 times the log of the number of channels, which gives us 47 dBm plus 10 times the log of 16 equals 59 dBm. This shows a 12 dB difference or offset between the composite power and the per channel power. Remember that composite power represents the total system output power, and it is always greater than the power per channel by this calculated offset based on the number of channels. Next, we need to calculate the free space path loss between the donor tower and the rooftop donor antenna, since this value wasn't provided directly. Given that we know both the frequency and the distance, we can use the standard free space path loss formula. The free space path loss in dB is equal to 36.6 plus 20 times the log of the frequency in megahertz plus 20 times the log of the distance in miles, which gives us 36.6 plus 20 times the log of 855.5 megahertz plus 20 times the log of 2.5 miles equals 103 dB. Next, we can calculate the BDA downlink input power using the following formula. The BDA downlink input power is equal to the radio tower ERP minus the free space path loss plus the donor antenna gain minus the transmission line loss, which gives us 47 minus 103 plus 9 minus 3 equals negative 50 dBm per channel. As we noted earlier, there is a 12 dB offset between channel power and composite power. Therefore, the BDA composite input power is 12 dB higher, or negative 38 dBm. Next, we can calculate the required BDA downlink gain needed to achieve the maximum channel output power using the following formula. The BDA downlink gain is equal to the BDA composite output power minus the BDA composite input power, which gives us 33 dBm minus negative 38 dBm equals 71 dB of gain. Next, we must determine the BDA downlink output power per channel. This can be calculated in two different ways. You can use the following formula. The BDA output power per channel is equal to the BDA downlink input power per channel plus the BDA downlink gain, which gives us negative 50 dBm plus 71 dB equals 21 dBm. Alternatively, we can use the formula the power per channel is equal to the maximum BDA downlink composite power minus 10 times the log of the number of channels, which gives us 33, minus 10 times the log of 16 equals 21 dBm. Again, there is a 12 dB offset between the channel power and composite power levels. If we remember the offset, we do not have used the formula. Next, we calculate the portable radio received signal strength. It's important to note that only a single channel measurement is taken. A radio measures the signal strength on its tuned channel, not the total composite power. Once the BDA gain has been set based on the composite power, we can disregard the composite value and focus solely on the per-channel power level. To calculate the near radio received signal power, we use the formula. The near radio received signal power is equal to the BDA output power per channel minus the passive DAS loss minus the near path loss, which gives us 21 dBm minus 15 dB minus 43 dB equals negative 37 dBm. Similarly, to calculate the far radio received signal power, we use the formula. The far radio received signal power is equal to the BDA output power per channel minus the passive DAS loss minus the far path loss, which gives us 21 dBm minus 15 dB minus 74 dB equals negative 68 dBm. Next, we will perform an uplink link budget. The uplink link budget traces the signal path from the portable radio transmitter to the public safety communications tower, estimating the signal strength received by the radio tower from both the near and far radios within the building. Starting on the right of the diagram, the portable radio transmits a signal from its antenna at a fixed power level. This is the starting point of the uplink link budget. The radio transmit power is typically provided by the local AHJ or system licensee and could be given in watts or dBm. For link budget calculations, all values should be in decibels, either dB or dBm. If the portable transmit power is provided in watts, it must be converted to dBm. Next, we consider near and far path losses between the radios and the indoor antennas. The near path loss represents the loss between an indoor antenna and a portable radio located close to it, resulting in the strongest uplink signal seen by the BDA. The far path loss represents the loss between an indoor antenna and a radio located in the most distant area served by that antenna, resulting in the weakest uplink signal seen by the BDA. The far distance depends on the building layout and system design. The near and far path loss values are the same as the values used in the downlink link budget. Next, we account for passive DAS losses. We will use an average DAS loss, the same used in the downlink link budget. Next, we have the BDA, which amplifies the signal and provides gain in the uplink path. The BDA uplink gain should be optimized using the formula. The BDA uplink gain is equal to the desired BDA output power minus the BDA input power. Following the BDA, we account for donor antenna transmission line loss, which includes losses from the coaxial cable and passive components, such as lightning arresters between the donor antenna and the BDA donor port. We will use the same transmission line loss as in the downlink link budget. Next, we have the donor antenna. The donor antenna provides gain specified in the manufacturer's datasheet as either dBd or dBi. We will use the same donor antenna gain as in the downlink link budget. Next, we calculate the free space path loss, or FSPL, using the known frequency and distance between the tower and donor antenna. We will use the same free space path loss previously calculated in the downlink link budget. By determining all the values shown on this slide, you can accurately calculate the uplink link budget. To determine the uplink signal strength received by the radio tower from near and far portable radios, we will break the calculation into distinct steps. For this analysis, we'll need to know the minimum received signal strength required by the radio system licensee. For example, the radio system licensee may require uplink signals to arrive at the radio tower above -95 dBm. First, we calculate the BDA near and far, maximum and minimum, uplink channel input powers respectively. Next, we determine the minimum BDA uplink channel output power required from the far radio to reach the radio tower at the minimum receive level. Using these values, we then calculate the required uplink gain needed to amplify the minimum or far BDA input signal to the minimum BDA uplink output level. Finally, we calculate the maximum BDA uplink channel output power and maximum received signal strength at the radio tower from the near radio. To calculate the minimum BDA uplink input power from the far radio, use the following formula. The minimum BDA uplink input power is equal to the radio output power minus the far path loss minus the passive DAS loss. To calculate the maximum BDA uplink input power from the near radio, use the following formula. The maximum BDA uplink input power is equal to the radio output power minus the near path loss minus the passive DAS loss. To calculate the minimum BDA uplink output power from the far radio, use the following formula. The minimum BDA uplink output power is equal to the minimum radio tower received level plus free space path loss minus donor antenna gain plus transmission line loss. You'll notice that in this step we subtract gains and add losses. This is intentional. Because we are working backward from the minimum signal level required at the tower, the direction of the calculation reverses, so gains are subtracted and losses are added. We calculate the required BDA uplink gain based on the far radio using the following formula. The BDA uplink gain is equal to the minimum BDA uplink output power minus the minimum BDA uplink input power. To calculate the maximum BDA uplink output power from the near radio, use the following formula. The maximum BDA uplink output power is equal to the maximum BDA uplink input power plus the BDA uplink gain. To calculate the maximum radio tower received signal strength from the near radio, use the following formula. The near radio tower received signal power is equal to the maximum BDA uplink output power minus the transmission line loss plus the donor antenna gain minus the free space path loss. Now we're ready to walk through a complete uplink link budget example. The purpose of the uplink link budget is to trace the signal path from the portable radio transmitter to the public safety communications radio tower, estimating the signal strength received by the radio tower from both the near and far radios within the building, ensuring they are within the radio system licensee's required limits. Refer to the diagram on the screen showing a typical public safety BDA system. To complete a full uplink link budget, the following input parameters are required. The frequency, the free space path loss to the donor site, the donor antenna gain, the cable loss between the BDA and the donor antenna, the BDA maximum uplink composite power, the passive DAS loss, the near and far radio path losses, the portable radio transmit power, and the radio tower minimum required received signal strength. For this example, the input parameters are listed in the box at the top right of the screen. You will notice that many parameters in the uplink link budget have the same values as in the downlink link budget. For simplification, we will assume only one portable radio is transmitting within the building at any given time on a single radio channel. The frequency we will use is 855.5 MHz, the same control channel frequency from the downlink link budget. We could choose to use the exact uplink frequency for the calculation, but the minor change in frequency and free space path loss has little impact on the result. So the free space path loss will also be the same value as the downlink link budget, which is 103 dB. The donor antenna gain is 9 dBd. The cable loss between the BDA and the donor antenna is 3 dB. The BDA maximum uplink composite power is 1/2 watt. The passive DAS loss is 15 dB. The near and far radio path losses are 43 and 74 dB, respectively. The portable radio transmit power is 1 watt, and the radio tower minimum required received signal strength is -95 dBm. The radio tower minimum receive level and the portable radio transmit power parameters are typically obtained from the local radio system licensee, or AHJ. We'll use the diagram on the slide as our guide, filling in each value as we move step by step from the near and far portable radios on the right to the radio tower receiver on the left. We'll begin by entering all known input parameters. The missing value is the portable radio transmit power. We can't enter a power of 1 watt directly, as power levels in link budgets are expressed in dBm. Converting 1 watts to dBm gives 1 watt equals 30 dBm. We'll use 30 dBm as the portable radio transmit power. Next, we calculate the near and far uplink input powers to the BDA. The near radio BDA input power will be the maximum BDA input power. The far radio input power will be the minimum BDA input power. The minimum BDA uplink input power can be calculated using the following formula. The minimum BDA uplink input power is equal to the portable radio output power minus the far path loss minus the passive DAS loss, which gives us 30 dBm minus 74 dB minus 15 dB equals negative 59 dBm. The maximum BDA uplink input power can be calculated using the following formula. The maximum BDA uplink input power is equal to the radio output power minus the near path loss minus the passive DAS loss, which gives us 30 dBm minus 43 dB minus 15 dB equals negative 28 dBm. Next, because we were given the minimum required radio tower input level of negative 95 dBm, we can calculate the minimum uplink output power from the BDA to reach the tower at that level. We use the formula, the minimum BDA uplink output power is equal to the minimum radio tower received level plus the free space path loss minus the donor antenna gain plus the transmission line loss, which gives us negative 95 dBm plus 103 dB minus 9 dBd plus 3 dB equals positive 2 dBm. Next, now that we know both the minimum BDA input power and the minimum BDA output power, we can calculate the required BDA uplink gain using the following formula. The BDA uplink gain is equal to the minimum BDA uplink output power minus the minimum BDA uplink input power, which gives us positive 2 dBm minus negative 59 dBm equals 61 dB. Next, now that we have calculated the BDA uplink gain, we can apply that gain to the maximum BDA uplink input signal to determine our maximum BDA uplink output power. We use the formula, the maximum BDA uplink output power is equal to the maximum BDA uplink input power plus the BDA uplink gain, which gives us negative 28 dBm plus 61 dB equals 33 dBm. However, this is where we need to be cautious. An output of 33 dBm corresponds to 2 watts, but the system parameters specify that the BDA's maximum composite uplink output power is only 0.5 watts or 27 dBm. The BDA cannot exceed this rating. Therefore, applying 61 dB of gain would push the output 6 dB above the allowable limit. The BDA's automatic gain control, AGC, will reduce the gain from 61 dB to 55 dB to cap the output at 27 dBm. In summary, the maximum BDA uplink output power in this case will be 27 dBm, which is the BDA's rated composite uplink limit. Finally, we can calculate the maximum received power at the radio tower using the following formula. The maximum radio tower received power is equal to the BDA maximum uplink output power minus the transmission line loss plus the donor antenna gain minus the free space path loss, which gives us 27 dBm minus 3 dB plus 9 dBd minus 103 dB equals negative 70 dBm. The final link budget that we will perform is the uplink noise power link budget. Before we can perform this link budget, we need to have a thorough understanding of how to calculate thermal noise power for different bandwidths. This was covered in detail in the noise and SNR module, but we will have a quick refresher now. Thermal noise is noise that is a result of the thermal agitation of electrons. The thermal noise power depends on the bandwidth and temperature of the surroundings. The formula for thermal noise is thermal noise power in dBm equals 30 plus 10 times the log of kTb, where k is the Boltzmann constant and is equal to 1.3807 times 10 to the negative 23 joules per Kelvin. T is the ambient temperature in Kelvin, and B is the bandwidth in Hertz. So let's look at an example. What is the thermal noise power in a 1 Hz bandwidth at standard room temperature of 293 Kelvin? We can simply input the values into the thermal noise power formula, which gives us the noise power in dBm equals 30 plus 10 times the log of 1.3807 times 10 to the negative 23 times 293 times 1 equals negative 174 dBm. Instead of performing these calculations by hand or by using a calculator, it can be convenient to create an Excel spreadsheet tool with formulas already built in, so you can quickly perform the calculations for different bandwidths and temperatures. Furthermore, there are thermal noise power calculators online which are available for free by performing a quick web search. Some of the most common thermal noise levels that we deal with when planning and designing public safety BDA systems are shown in green. It is recommended to memorize these thermal noise levels. Now, since we know the thermal noise power of a 1 Hz bandwidth is equal to negative 174 dBm, we can use the following formula to calculate the thermal noise power over any bandwidth while assuming a standard room temperature. The formula is the noise power in dBm is equal to negative 174 dBm plus 10 times the log of the bandwidth in Hertz. So let's look at an example. What is the thermal noise power in a 12.5 kHz bandwidth? We can simply input the values into the alternate thermal noise power formula, which gives us the noise power in dBm equals negative 174 dBm plus 10 times the log of 12,500 Hertz equals negative 133 dBm. The noise factor is defined as the ratio of actual output noise of a device to that which would remain if the device itself did not introduce noise. Or in other words, the ratio of input signal to noise ratio to output signal to noise ratio. On the other hand, the noise figure is the noise factor expressed in decibels. The noise figure specifications of a BDA should be listed on the manufacturer's datasheet. This information is required to perform a proper noise link budget. Let's look at an example. A BDA has a gain of 70 dB and a noise figure of 5 dB. Assuming KTB of negative 133 dBm and an input signal of negative 69 dBm, what is the output signal strength, output noise power, and output SNR? The output signal strength is equal to the input signal strength plus the gain of the device, which gives us the output signal strength is equal to negative 69 dBm plus 70 dB equals positive 1 dBm. The output noise power is equal to the input noise power plus the gain of the device plus the noise figure of the device, which gives us the output noise power is equal to negative 133 dBm plus 70 dB plus 5 dB equals negative 58 dBm. The output signal to noise ratio is equal to the output signal strength minus the output noise power, which gives us the output SNR is equal to positive 1 dBm minus negative 58 dBm equals 59 dB. When talking about thermal noise of a public safety radio system, it is common to refer to the thermal noise floor as KTB, and this value is going to be negative 133 dBm for a 12.5 kHz bandwidth radio channel. However, it is important to understand that thermal noise and BDA input noise are not the same thing. Every building has the potential to generate environmental noise throughout from different electrical devices commonly found in buildings. These devices can raise the RF noise floor within the building, potentially leaking into the antennas system and feeding into the BDA. If the environmental noise reaches the uplink input above the thermal noise level, it will be amplified accordingly, and excessive noise output will be present. Noise and interference sources within a building need to be identified and isolated so the noise they generate does not get retransmitted by the BDA. It is important to perform an RF site survey to determine any sources of noise within the building. Furthermore, it is important to measure the BDA uplink input noise from the DAS before commissioning and turning on the BDA system, to ensure you will not amplify unwanted noise and create a widespread interference problem when the BDA is activated. Finally, an increased noise floor inside a building can affect your uplink SNR and cause degradation of radio performance. Now we are ready to walk through a full uplink noise link budget example. The purpose of the uplink noise link budget is to ensure the system will comply with FCC noise emissions rules and to confirm the generated BDA noise will not raise the noise floor of the donor site receiver. Refer to the diagram on the screen showing a typical BDA system. To complete a full uplink noise power link budget for a public safety BDA system, we need the following inputs: the average building noise level, the average passive DAS loss, the target BDA uplink gain, the BDA uplink noise figure, the cable loss between the BDA and the donor antenna gain, and the free space path loss to the donor site. If the building noise level cannot be measured, you can assume a building noise level which is equal to thermal noise level. However, when implementing the BDA system, you must measure the BDA uplink input noise before commissioning and turning on the BDA to validate the link budget and confirm excessive building noise does not exist. To calculate the uplink noise power the radio tower site will receive from the BDA system, we need to break the calculation down into 3 separate pieces. First, we must calculate the BDA input noise power. Next, we must calculate the BDA output noise power. Finally, we can calculate the radio tower received noise power. To calculate the BDA input noise power, we can use the following formula. The BDA input noise power is equal to the building noise power minus the passive DAS loss. The BDA input noise must be greater than or equal to the thermal noise power level. It is important to remember that the noise level cannot decrease below the thermal noise level. When the building noise power level decreases in strength as it passes through the DAS, when it reaches the BDA input, the minimum noise level that it can arrive to the BDA input is the thermal noise level. In other words, the passive DAS losses cannot attenuate the noise level below the thermal noise level. If the passive DAS loss is enough to reduce the noise signal strength to the thermal level, then the BDA input noise power will be equal to the thermal noise level. Next, to calculate the BDA output noise power, we can use the following formula. The BDA output noise power is equal to the BDA input noise power plus the BDA uplink gain plus the BDA uplink noise figure. Finally, to calculate the radio tower received noise power, we apply the following formula. The radio tower received noise power is equal to the BDA output noise power minus the transmission line loss plus the donor antenna gain minus the free space path loss. In this calculation, it's important to recognize that the resulting value may sometimes fall below the thermal noise floor. While the actual noise level cannot be lower than thermal noise, we present the theoretical value to illustrate the margin or headroom relative to that limit. In large jurisdictions where hundreds or even thousands of BDAs may be deployed, the cumulative noise from multiple devices can combine and elevate the overall noise floor at the donor site. To account for this potential aggregation, some radio system licensees, or AHJs, may require that the donor site be targeted with a theoretical noise level below the thermal noise floor, ensuring sufficient headroom for future BDA expansion. This concept will be further clarified in the example on the next slide. Now, let's walk through a full uplink noise power link budget example. The input parameters are listed in the box in the top right corner of the screen. The building noise level is negative 122 dBm measured over a 10 kHz bandwidth. The passive DAS loss is 15 dB. The BDA uplink gain is 75 dB. The BDA uplink noise figure is 5 dB. The transmission line combined loss is 3 dB. The donor antenna gain is 9 dBd. The control channel frequency is 855.5 MHz. And the donor tower site is 2.5 miles away from the rooftop donor antenna. We will use the diagram on the slide as our link budget guide and fill in the blanks as we work through the link budget from the right side to the left side. We will start by entering all of the known input values that were given to us. The first step is to calculate the free space path loss between the donor tower and the rooftop donor antenna, as this information was not directly given to us. Since we know the frequency and the distance, we can apply the free space path loss formula, which gives us the free space path loss in dB is equal to 36.6 plus 20 times the log of 855 megahertz plus 20 times the log of 2.5 miles equals 103 dB. Next, we can calculate the BDA input noise power. The BDA input noise power is equal to the building noise power minus the passive DAS loss, which gives us negative 122 dBm minus 15 dB equals negative 137 dBm. The thermal noise level for a 10 kHz wide bandwidth is negative 134 dBm. Since our calculated value of negative 137 dBm is below the thermal level, we will use the thermal noise level as our BDA input noise power level. This will not always be the case if we have a high building noise level. Next, we can calculate the BDA output noise power. The BDA output noise power is equal to the BDA input noise power plus the BDA uplink gain plus the BDA uplink noise figure, which gives us negative 134 dBm plus 75 dB plus 5 dB equals negative 54 dBm. Finally, we can calculate the radio tower received noise power. The radio tower received noise power is equal to the BDA output noise power minus the transmission line loss plus the donor antenna gain minus the free space path loss, which gives us negative 54 dBm minus 3 dB plus 9 dBd minus 103 dB equals negative 151 dBm. That concludes this module. Thank you for watching this presentation of Comba University.